In this third video of module 3, we will first learn the theorem of Pappus Guldinus. So there are actually two theorems by Pappus Guldinus. One is for finding the surface area and the next one for finding the volume. So some basic theory that the theorems of Pappus Guldinus were first put forward by 300 AD and it was proposed initially by Pappus and then it was restated by a Swiss mathematician Guldinus by 1640. So these theorems offer a simple way of computing the area of surface of revolution as a theorem 1 and the volume of bodies of revolution as a theorem 2. So these theorems both are very simple theorem. So the first one states that a surface of revolution is a surface which may be generated by rotating a plane curve about a fixed axis. So you can see here a axis AC is here and you have a semicircular curve. So by revolving this semicircular curve about the AC axis, you will get the surface area of a sphere, right? Similarly, for the AC baseline, you have the AB curve. Revolving the AB with respect to AC, you will get the surface of a cone. If you could imagine, as you already learned the graphics classes. Then we have the ring. We have a closed curved area, and when you revolve this about AC, you get a tube surface area. And for a straight line parallel to the base axis, once you get revolved about AC, you will get the surface area of a cylinder. So the surface of a sphere is obtained by rotating the semicircular arc ABC about the axis AC, cone by this inclined line about AC, and surface of a ring by rotating the circumference of a circle about the axis AC, and also surface of cylinder by rotating the horizontal line, which we have just explained. So this is a proof of the theorem 1. So how to find the surface area? So the area of a surface generated by revolving a plane curve about a non-intersecting axis. That means that suppose we are considering a horizontal axis, the proposed or the assumed curve should not intersect with the horizontal axis. Okay, intersecting axis in the plane of the curve is equal to the product of length of the curve and the distance traveled by the centroid of the curve while the surface is being generated. So say you have a curve like this. Okay, assume only one side, and when this curve is rotating about y-axis, okay, then the total length over which this is revolving will give you the surface area. So coming to the proof, consider an element of length dl. So you have the length of the curve here and dl of the curve of length L, which is revolved about the x-axis. So we have the horizontal x-axis and the curve is revolving. The area generated by the element is equal to 2 pi into y dl. So this y into dl, y is actually the centroid of the assumed curve from the base axis, and dl is the length considered. Therefore, the entire area generated by the curve, we have to actually integrate it over the length to give surface area is equal to integral over 2 pi into y into dl, where it is approximately similar to the 2 pi r perimeter into the like the length. Okay, 2 pi will the perimeter into the length or height will give you the entire surface area. So 2 pi into integral over y dl, we can take as y bar into L on integration. 2 pi into y bar is the distance traveled by the centroid of the curve of length L. So A is equal to 2 pi into y bar into L. The problem, obtain the expression for the area of surface generated by rotation of a semicircular arc of radius r about an axis passing through its endpoint. So we have the axis which is given in the dotted line format, and you have the semicircular arc ABC, and this ABC is rotating with respect to the baseline. So please note that we don't know actually the or you haven't studied the centroid for this arc. What you know is that you know the centroid of the semicircular area. So we need to find it out. So to find that, we have the we can divide this, or we can consider this semicircular arc, and the let the radius be r, y bar be the centroid point, and we have for a small angle d theta, we're considering a small length as a dl. So d theta is equal to opposite theta by r, right? So d theta is equal to dl by r. So dl is equal to r into d theta. We know this relationship. So y bar, to find it out, y bar is equal to, because x bar we don't need, and as well as x bar will be on actually on this x-axis, right? So the y bar, which is unknown to us, is equal to integral of y into dl by integral dl. We know the expression for pi. So integral over 0 to pi r sine theta into r d theta dl divided by integral 0 to pi r d theta, because the 0 to pi means we are actually the integration ranges from 0 to 180 degree. So for integration we'll get it as 2r by pi. So now remember that for the centroid of this semicircular area it was 4r by 3 pi. So for this semicircular arc it is 4r by pi, sorry, 2r by pi. And so by applying the Pappus-Guldinus theorem 1, distance of centroid of semicircular arc is 2r by 3 pi from this midpoint. So this y bar is 2r by 3 pi, sorry, 2r by pi. And the length of ABC, we know that the length is pi r. So this length into the centroid value will give you the total surface area generated by this revolution. Okay, actually we are revolving this semicircular arc with respect to this base, so that by revolving we'll get the surface area of a sphere, which is 2 pi into 2r by pi is equal to 4r. Okay, hence the area of surface generated is pi r into 4r is equal to 4 into pi r square. Yeah, so the distance traveled by the centroid alone in one revolution will be equal to 2 pi into 2r by pi. That means that we know that the centroid is at a distance of 2r by pi from this baseline, and considering a point here, and this point is revolving with respect to the horizontal axis, we have 2 pi r, right? 2 pi into the point r will be that for centroid 2r by pi. So this 4r is the total rotation distance made by the centroid alone, and that into the this semicircular perimeter, right? Perimeter will give you the area of surface generated, which is equal to 4 into pi r square. So the next problem, calculate the surface area obtained by revolving the line ABC. So we have find the surface area obtained by revolving the line ABC. A is here, B is here, C is here, as shown in figure about y-axis and x-axis separately. We have horizontal x-axis here, and this is your y-axis, right? So coming to that, first we need to find the total perimeter of this individual shape, which is the length of the line is equal to 18 is given as the altitude, 9 is given as the base, and hypotenuse by root of 18 square plus 9 square, 47.1 as the total perimeter of this triangle, and distance from centroid of y-axis. So we know the value, and the value is 2.78. No, actually, there is a difference with the previous problems you did. That means we are considering here only a single line, not an area. So the equations like h by 3, b by 3, which you directly obtain for the planar area cannot be applied here. You uh, should treat the individual components as line element, right? So in that case we have so this is a ab is a single line, then bc is a single line, and ca is a single line. So that is why l1 18 into 0, because we are taking with respect to the y-axis, right? 18 into 0 plus 9 into 4.5 centroid from the vertical axis, plus 20.1 is the hypotenuse we obtained into 4.5, because actually this maximum is 9 and minimum is 0. So the centroid will be at this point, which is 4.5, divided by total length is 47.1, which is 2.78, and the distance traveled by the centroid in one revolution. We are considering the centroid as 2.78, right? So this from this axis 2.78 distance. So 2 pi into 2.78 is a total rotation made by the centroid, and the area of surface generated is total rotation made by centroid, that is 2 pi into 2.78 into the individual perimeter of this uh, shape, right? This line shape. So it is 822.71 centimeters square. So again, now we are finding the distance of the centroid from the x-axis. Okay, so similarly, to find the like the surface area generated with respect to the x-axis, we have a similar calculation for centroid from the x-axis y into L1 plus y into L2 plus y3 into L3 by all the length. So we are considering, yeah, we have the figure here also. So y into L1. So we have the 9 centimeter here. So 9 is a distance of 18 centimeter from the baseline. 9 into 18 plus 18 line is having the midpoint at 9. So 18 into 9 plus 20.1 is this inclined line, and this inclined line so here actually the centroid is here, right? So it was like 4.5 from the left axis, and from the bottom axis the value is actually 9 centimeter, which is exactly the middle of the total line. So it is 10 9. So we get 10.72 as the centroidal value. So we will get the centroid of total. This total line shape is a distance of 2.78 horizontally and 10.72 centimeter from the bottom. So it may be approximately at yeah, 9 is here, right? So it may be approximately at this point. Okay. So similarly, distance calculated, oh, sorry, traveled by centroid in one revolution is 2 pi into r. So it is 10.72 the centroid, and we get the area of surface generated, total length perimeter into the distance traveled by the centroid as 3172.46 centimeters square. So that Pappus-Guldinus theorem was to find the surface area generated by revolving a plane curve, and next we have the calculation for the volume. So as per this theorem, the volume of a body generated by revolving a plane area. So here we are focusing on the plane area. So you can directly use the centroidal values which we have studied in the classes 1 and 2 of this module. Plane area about the non-intersecting axis, and the plane of the area is equal to the product of area and the distance traveled by the centroid. So please see the similarity. The theorem 1, it was actually to find the surface area. So you need only the length of the curve and the rotational distance. For finding the volume, definitely there should be an area multiplied by the total rotation. So we have the product of area. Then this is same. Distance traveled by centroid is common for both the theorem 1 and theorem 2. For the previous one, it was the length of the line. For this theorem, it is the product of the area. So the body of revolution is a body which is generated by rotating a plane area about a fixed axis. Similar figures to the previous, but this is actually an area which is given a hatched form. A solid sphere is generated by rotating a semicircular area. A cone by rotating the triangular area. So you can visualize by rotating the semicircular area with respect to the base, you will get the complete sphere. And by this, you will get complete cone. And by this, we will get the tube, complete tube. Previously, it was a hollow tube. And by this one, you will get the complete cylinder, which having a volume. Here the derivations. Consider an element dA. We have the ring-like uh, shape here, and we're considering a dA, elemental area of area A, which is revolved about the x-axis. We are revolving it around the x-axis, and the volume dV generated by the element dA in one revolution is 2 pi into y into dA. Yeah. Therefore, the entire volume generated by A is equal to integral 2 pi into y dA is equal to 2 pi into y bar into A. So it is the distance traveled by the centroid of the area, the 2 pi into y bar. Because y bar is a single value, into 2 pi will give you the total distance covered by the centroid, into the area will give you the total volume of the shape formed. A problem which will make you clear. Obtain an expression for the volume of the body generated by a revolution of a semicircular area when its base is in touch with the axis of rotation. So we have the area here. Directly we know that the centroid from the baseline is 4r by 3 pi. So we have the following inputs. Area of semicircle we know pi r square by 2. Distance of centroid axis we know that 4r by 3 pi. Distance traveled by the centroid alone will be this centroid value into 2 pi. So 2 pi into 4r by 3 pi, 8 by 3 r is the total uh, rotational movement made by the centroid alone into the surface area. It is this area will give you the total volume of sphere, which is equal to 4 by 3 pi r cube. So this is actually a validation or proof of the real value. Similarly, the cone expression, obtain expression for the volume of body generated by revolution of a triangle, which is when its base is h, and also it is touching the axis of rotation. The length of the other side is r. Right. So you know that the area of triangle half into h into r. Distance from base is 1 by 3 into r. See, please note that this is an area. As is given, this is an area, not a like a line figure. So 1 by 3 into r, which is known to you. Distance traveled is 2 pi into 1 by 3 into r, which is 2 by 3 pi r is the distance covered by the centroid along on revolution. Into the area of triangle will give you the 1 by 3 pi r square h, which is the volume of the cone. The next important topic in this module is the moment of inertia. It is actually a purely a mathematical term which gives a quantitative estimate of the relative distribution of area with respect to some reference axis. So here we have taken a reference axis x here and y here. So it's about the distribution of this area with respect to a particular axis considered. So this moment of inertia value will vary when we are taking a different axis. It's very important for the first information. So consider an element area dA which is located at a distance of y from x-axis. X is here and y is here. Yeah, and x from y-axis. Okay. The second moment of elemental area about x-axis is y square into dA. Second moment is actually y into dA into y. So this y square dA, because like the in say first moment will be the dA into y. You know that the moment that is the uh, area into lever arm. dA into y will be the first moment of elemental area. Second will be the again it is multiplied by the distance. So y square into dA. Similarly, s square dA4 with respect to y-axis. So for the entire area, I-axis is equal to integral y square dA and Iyy is equal to integral s square dA. As we have considered only a small area here, for the entire area, the value is integration. Okay. Generally, the moment of inertia of an area is called the area moment of inertia, another term, or second moment of area. The moment of inertia is of a physical body is called the mass moment of inertia. So here we are considering an planar area to find the moment of inertia. If it is a physical body which has got a depth parameter also, it will be a mass moment of inertia. The axis passing through the centroid is called as the centroidal axis, and the moment of inertia about the centroidal axis is denoted by Ig. So this was the thing I explained before. So there is the moment of inertia. It varies with respect to the selecting axis. So this is an axis which is actually separated far away from the uh, planar area considered. For the axis which is passing through the proper centroid of the planar area, it is called as the centroidal moment of inertia denoted by the Ig. So the Igxs and Igyy. Another important theory part is the radius of gyration of an area. So you can consider two areas here, area 1 and area 2. Consider an area A which has the moment of inertia I. We are denoting moment of inertia by I. With respect to the reference axis AB, we have the AB here, and this is the planar area which is having a moment of inertia I. Let us assume that this area is compressed into thin strips. So same area, it is compressed to a strip area like this, which is also parallel to AB. For this strip, to have the same moment of inertia I with respect to the same reference axis AB, the strip should be placed at a distance of k from the axis AB such that I is equal to A into k square, where k is the radius of gyration of the area with respect to the given axis. So please note that the moment of inertia value will increase when it is located far away from the considered axis. So by comparing these two areas, you know that this area is actually more near to this AB line, and this is actually far from the uh, AB line. So there will be a particular value for the K, so that the moment of inertia of both this area with respect to this baseline will be equal. So that value is called as the radius of gyration of a particular area. Thus, the radius of gyration of an area or even a body may be defined as the distance from the axis of reference where the all mass or area of a body is assumed to be concentrated. Another important theorem is the perpendicular axis theorem. That is, we discussed regarding the y-axis moment of inertia, iyy moment of inertia about y-axis, moment of inertia about x-axis. Okay, are the moment of inertia of an area A about mutually perpendicular axis x's and yy in the plane of the area. Then the moment of inertia of the area about the z axis, which is perpendicular to this plane, right? Maybe for the screen you consider mobile screen or the laptop screen, perpendicular to a screen you have the third axis x z axis. So for that z axis I z is equal to I xs plus I yy. A simple derivation, the same figure you considered before. So you have I z is equal to integral r square into dA, where r is actually the distance uh, to the third axis, z axis, which is actually perpendicular to the screen. So we can divide that the r square is equal to s square plus y square, and so we have the when on dividing we have I z is equal to I xs plus I yy, where I xs, sorry, z is called as the polar moment of inertia. So similar to the perpendicular axis theorem. Perpendicular means for a perpendicular axis, z, what is the value? It's a combination of sum of values of x and y, right? And for the parallel axis theorem, transfer theorem, it states that the Ig is the moment of inertia of a plane lamina of area A about centroid axis. We have defined this Ig previous, right? So this was the Ig through the centroidal axis. Okay, if Ig is the about centroidal axis, then the moment of inertia about any axis, we are considering a different axis, different line of axis, which is parallel to the centroidal axis at a distance of h, then the total IAB is equal to IG. IG is for the individual area about centroidal axis plus area of the plane considered into the S square is distance from the centroid of planar figure to the axis considered. This will give you an idea. That is, we have the area here considering a small dA. So the IgG is Ig is with respect to centroid axis. Like this is one line and this is one line, and we have to shift the value. We have to find the value with respect to AB. In that case, the value will be Ig for the individual area plus area of this planar into the S square, which is from here to here. As a proof, consider an elemental area dA here at a distance of y from the centroid axis. So from centroid axis y, the first moment of elemental area about the axis is equal to dA into y plus h. So h is centroid to the considered axis, y is the respective value, centroidal value from the centroidal axis. So y plus h. Second moment of inertia, again squaring dA into y plus h all square. So on expanding and the second moment of inertia of entire area is on integration we will get dA into y plus h all square, so a plus b all square. On expanding we have y square into dA plus integral s square into 2a plus 2hy into dA. So we know that the y square dA, which is actually with respect to the centroid axis, so Ig and h square dA and 2hy dA. So Ig is equal to h square a integrating dA a plus 2h into a into y bar, right? So this will give you the, but y bar is 0 as it is distance, sorry, y bar is equal to 0 as it is the distance of the centroid from the axis. So we get IAB, that is with respect to the line AB, the moment of inertia is equal to moment of inertia of this individual planar area about its own centroidal axis plus area of this planar area into x square distance from baseline to the centroid of the considered planar area. Yeah, calculate the moment of inertia of a rectangular cross section about the centroidal axis. So we are finding about centroidal axis. Uh, we know that this is of b by 2 and d by 2 from the uh, x and y axis. So considering a area dy, yeah. So consider an elemental area. Uh, for that elemental area, we have the length dy, and this element of this thickness dy, the distance of y from the x-axis. So we have the centroidal x-axis here. Area of the element dA, total this area is equal to b, total width of the rectangle into dy. Elemental thickness will give you the total elemental area. Second moment of this elemental area about x-axis is equal to y square into dA. Y is actually distance from the x from, sorry, distance from the x-axis to this elemental area considered. So y square into b into dy. So ixs is equal to integral minus d by 2 to d by 2 y square into b dy. Upon integration, we will get that the value is p dq by 12. This is a important derivation, and you are required to use this moment of inertia value for different problems later on. Similarly, for finding the IYY, consider an element area in the actually in the y direction. So similar derivation will give you that the IYY is equal to dB cube by 12. So please note the similarity that for IXS about this horizontal axis, the moment of inertia is B, base into depth cube by 12, and for the y-axis actually the base in this one will change to the height in the next axis, right? So the for iyy this will change to d into b cube by 12. Hope you notice the similarity. And one important, yeah, so the moment of inertia of rectangular lamina about its centroid axis is equal to 1 by 12 into length of side parallel to the axis into length of other side all cube in another way. So moment of inertia about the base can be calculated. So this I x's and yy are with respect to the centroidal axis. So for to find the values moment of inertia with respect to this, maybe this baseline, maybe this line and this line, you need the parallel axis theorem. Hope you remember the parallel axis theorem where iab new axis is equal to ig, which we found now, plus a into x square, which we are going to use now. So for that, uh, I'm repeating the expression b d cube by 12, which is found now, plus b into d, total area of rectangle, into d by 2 all square. We're finding AB. AB is here. So we'll give you BD cube by 3. Manipulation of rectangular lamina about base is BD cube by 3. Another problem is to find the moment of inertia of a triangle about the centroid axis. So we know that for a triangle we have h by 3 and the b by 3. As this is actually a isosceles triangle with same inclined lines and different base width isosceles. So then the x bar will be exactly passing through the middle of this figure, planar figure, and y bar will be h by 3 from the base, right? So consider an element of thickness dy, a distance y from the vertex. Let the element, let length of this element be b, small b. Area of the element is b into dy. Second moment of this elemental area is given by y square into y is given here. So we have the determine the moment of inertia of a triangle about its centroid axis parallel to its base. So we have the centroid axis just given in the dotted line, and the base is actually PQ. Okay, so this IR is equal to integral 0 to h b into y square dy. We know by relation b by capital B is equal to this small y by total h. So b is equal to capital B by capital H into y. On substitution, we'll get the value as b h cube by 4. And now we are going to find the moment of inertia about the baseline, that is, just a minute. Sorry, here this is small correction. The correction is that here the initial expressions are of moment of inertia are performed with respect to the base r, this line. We will again reread this one. Consider an element of thickness dy, a distance of y from the vertex r, a distance of y from the vertex r. Let the length of this element be b, length is b, and area of element is ds equal to b in dy. Second moment of elemental area about axis through vertex r. So this is actually the vertex, and from here consider that the centroidal values or distance to this area is y. So dir is equal to y square into b dy. So ir is equal to integral of 0 to h b into y square dy. So this is b no, b by b is equal to y by h is equal to b is equal to b by capital H into y. We'll get IR, which is the moment of inertia of this triangular area with respect to the R, right? So it is obtained as b into h cube by 4. Now we need to find the Ig value, right? So the IR is equal to the Ig plus AH square, right? That is with respect to centroid is Ig plus AH square is with respect to the new axis, right? So Ig is equal to IR minus AH square. IR we obtained as BH cube by 4 minus this area half into B into H into 2 by 3 H all square, which is giving us that the Ig is equal to BH cube by 36 for the triangular planar area with respect to the centroid. Ig is equal to BH cube by 36. Then again using parallel axis theorem, so we initially found for the r axis, then we found about centroidal axis by the parallel axis theorem. We can again find for the pq axis. Ipq is equal to ig plus a square. Ig is known to you now, plus this area into h by 3. Now this from the centroid to the base it is h by 3, will give you bh cube by 12. So the moment of inertia of a triangular lamina about its base is bh cube by 12. About its centroidal axis parallel to base is bh cube by 36, and for the axis passing through the vertex, it is bhq by 4. So this is actually the important information, that the moment of inertia values will vary with respect to the axis selected, right? And please note that the value will be always low with respect to centroidal axis, and it will increase as the length as well as the distribution of area also changes, because the term is by sorry, by because that additional factor ig will be a constant factor. Because for IPQ as well as IR is equal to IG plus A square, right? So IG will be always a single value plus some parameter will be there for any axis other than the centroidal axis. So it depends square times the distance. The distance is increasing, it is increasing by square times, as well as it has some implications on the area also. So even this area is a constant value. This h square is actually, the h is dependent not on the actually what is h? The h is actually distance of the new axis from the centroidal axis. So it in a way it is dependent on the distribution of areas, because if the more areas concentrated at the bottom region, here the h will be less, so that this will having a lower value. If the h value is very high, then again the moment of inertia will be high value. This is certain reflections on the obtained values. Determine the moment of inertia of the circular lamina about its centroidal axis. So we have the circular lamina. Consider elemental area as shown in figure 2.80. The area of element is equal to dA is equal to r into d theta into dr. So dr is elemental thickness. R into d theta will be this value, and into dr will be the elemental area. Second moment of this elemental area about x-axis is equal to y square, which is the centroidal distance, into the dA, which is integral y square r into d theta dr is equal to integral over 0 to 2 pi in the perimeter, and 0 to r in the radial direction. So dual integration. Upon integrating, you will get the value as ixs about this centroidal axis. The value is pi into d raised to 4 by 64, which is same as the case of ixs, because it is symmetrical figure. The ixs and iyv will be same for the circle. And you know that the I is a distance. If you want to calculate, it will be the ixs plus iyy, which is equal to 2 times this value. Yeah, because symmetry, the value is same. We know that izz is equal to 2 into ixs, sorry, ixz is equal to ixs plus iyy. Determine the moment of inertia of semicircular lamina about centroidal axis. Same derivations. You could follow this, and you will find that the ixs is equal to 0.11 into r raised to 4. And moment of inertia of semicircular lamina about base is also obtained as pi into d raised to 4 by 128. So in the previous one, we found the moment of inertia of semicircular lamina about centroid axis. Centroid is, you know that for this area it will be 4r by 3 pi, right? So about centroid axis, and moment of inertia about centroid axis perpendicular to the base. So same value is obtained. Again for the quarter circle, similar derivations are there. And because of the symmetry in both the s direction and the y direction about the centroidal axis, the value of The IXS and IYV is 0.055 r is to 4.